Hello class. Today we are going to be learning about organic chemistry. Now, organic chemistry starts in the early 19th century, where a chemist, Jöns Jacob Berzelius, classified compounds as either being inorganic or organic. Organic being those derived from living things, inorganic being those derived from non-living things. Now, this all changed when Friedrich Wöhler produced an organic compound, urea, from two inorganic compounds. So the ability to generate organic compounds from inorganic materials. Later on, the famous Urey-Miller experiment actually showed that you could generate the components necessary for life given the conditions of our early atmosphere and our early oceans. So given inorganic components, the things that our early atmosphere would have been composed of, in the Urey-Miller experiment they were able to make RNA being one of the more complex molecules. So no longer could we say that it was simply just living things, although when we think organic compounds today we still think living things, but we've refined our definition to be compounds containing carbon. Now, there are a few exceptions to this rule. So carbon compounds that are carbon oxides, like carbon monoxide, carbon dioxide, those are inorganic. Carbonates, anything where you see like CO3 carbonate, that is inorganic. Carbides, cyanides, these are all inorganic carbon compounds, but other than these few exceptions, every carbon-containing compound is considered organic. Now, all organic compounds are covalent compounds as well, which means they do include a wide array of non-metal elements within the compounds. And unfortunately, this means that we have to have a very complex naming structure in order to identify what these compounds would look like at the molecular level. Now, there are absolutely millions of organic compounds, far more than inorganic, for a couple good reasons. One, carbon can easily bond to itself. Carbon can form carbon-carbon single bonds, right, sharing one pair of electron. They can form carbon-carbon double bonds, sharing two pairs, and they can form carbon-carbon triple bonds, sharing three pairs of electrons. They can bond easily, carbon that is, can bond easily to hydrogen, nitrogen, oxygen, sulfur. The main components of life. If we were to break down the elemental composition of your body, what are the main constituents? Well, it's mainly carbon, hydrogen, oxygen, but then after that it's nitrogen, phosphorus, sulfur. So carbon can easily bond to those other essential atoms necessary for life. Carbon compounds can form chains or rings. The carbon atoms can bond in a cyclic structure. This opens up a huge array of possible compounds. And I've already touched on this, they can form double and triple bonds. Now, it's because of this that when scientists look at life and they try to imagine what life could look like on other planets, alien life, they struggle imagining any life that is not carbon-based. Carbon is very special in that not only is it able to bond to all these different molecules, easily bond to itself, form double, triple bonds, all of these things, but it has how many valence electrons? How many valence electrons does it have? Look on your periodic tables. How many valence electrons does carbon have? It has 4 valence electrons, which means how many electrons does it need in order to be happy, in order to have a full shell? The answer is it needs 4 more. So carbon can form 4 covalent bonds as a result of this. So it can form a wide array of bonds, and it can form a lot of bonds. It can form 4 different bonds per carbon atom. So, how many valence electrons? It has 4. Would carbon and hydrogen make covalent or ionic bonds? Covalent, how many electrons can carbon share? 4. And how many bonds, single bonds, can it make? 4. So this aspect of carbon allows it to form a much more complex array of organic molecules, much more organic molecules than if life were based on, say, something else, like nitrogen or oxygen. How many valence electrons does nitrogen have? Has 5, right? It only needs to share 3 electrons. How many does oxygen have? It has 6. It only needs to share 2. So remember, there are Lewis dots here showing the number of valence electrons, right? Carbon needs 1, 2, 3, 4 more electrons to be happy. Hydrogen only needs 1 more electron to be happy and look like its nearest noble gas. So of these, take a look at your periodic tables, look at how many valence electrons there are, and think about, well, how many more does it need? A little grade 10 review. So how many different, how many covalent bonds could these compounds form? How many different single bonds could they have? Well, carbon can have 4, hydrogen 1, oxygen can make 2 single bonds, nitrogen can make 3, and your halides, your halogens, they can make 1. Now, hydrocarbons are going to be our main area of focus in this unit. They are the simplest hydrocarbons, and they're going to form the base of our naming system. So, hydrocarbons, in their simplest form, consist of just carbon and hydrogen. For example, methane, the simplest of all hydrocarbons, is just carbon bonded to 4 hydrogens. Now, hydrocarbons can come from living things. All living things produce hydrocarbons of varying degrees. Whereas one we explored in biology. If you took grade 11 bio, you learned a lot about, fats, for example. What is a fatty acid? Well, it's effectively just a long hydrocarbon chain with a carboxylic acid group on one end. Another source in our day-to-day lives is fossil fuels. Dead things that were compacted over geological time and turned into what we know today as fossil fuels. And lastly, we can synthesize them. I'm sure, those of you that are driving, when you get an oil change, you have the choice of synthetic versus conventional. Right? Conventional oils in your car would be from fossil fuel sources, whereas synthetic, it's in the name, it's oil that is synthesized, tends to be slightly better for your engine because it's more uniform, less contaminants, but it is more expensive to produce. So in your notes booklets, there is a little reading assignment on hydrocarbons. I briefly just want to talk about how we separate hydrocarbons. How do we separate different mixtures of compounds? Well, when we refine hydrocarbons, we will use something called distillation, fractional distillation in this case. So as we're heating our solution up, we reach the boiling point of our gases first, our low boiling point substances in solution. And as these things boil off, what do you think happens to our temperature? Well, our temperature stays the same until all of it is boiled off. Once all of it is boiled off, then the temperature will rise until the next substance starts to boil off. It is this principle by which we will fractionally remove all of the different components of that oil. And this produces all of your products from gasoline, which is in that octane range, right? That 8 carbon-ish range, all the way up to things like paraffin waxes or greases, which have 18 or more carbons in their chain. Now, another area we use distillation is in making alcohol. For example, we will brew our alcohol, right? It'll be very low alcohol concentration in the whatever 7-8%, and then we can boil off the ethanol because it has a lower boiling point than water, and distill it, making your spirits and your concentrated alcohols. All right, so let's briefly talk about structure. Now, there are tons of different types of hydrocarbons, since you can always add another carbon and you can rearrange the existing carbons in new ways. In fact, the more carbons you have, the more ways you can rearrange those carbons. So there is almost infinite possibilities. Recall for a second allotropes. Those are going to be the same substance but different crystalline structures. Remember the whole discussion we had about graphite versus diamond? Those are allotropes, but something we will be focusing on in this unit is isomers. Isomers have the same molecular formula, but they have a different structural formula. Right? The atoms are bonded together in a different way. So isomers will be a big focus of this unit. Looking at an example, here we have C5H12, 5 carbons, 12 hydrogens. We could arrange them in this way, but we could also arrange them in this way. If you counted the atoms here, you would see that they are equal to one another. They have the same molecular formula. However, this one here is arranged differently than this one, and thus it does have different physical and chemical properties. Now, when we are talking about how we draw molecules, how do we draw those structures, there are different ways we can do that as well. Now in this course, I probably won't be doing complete structural diagrams too much. And the main reason is it just takes a lot of time. The more you study organic chemistry, the more you will move towards line drawings. Most of what I'm going to do in this unit is going to be condensed structural diagrams. But if you take organic chem at a university level, most of what you're going to see is going to be these line diagrams here. Now, what is the difference? Well, the line diagrams doesn't show any hydrogen bonds, and each of these little nodes here, where the two lines meet, represents a carbon atom. So all of these are showing the exact same thing, just for simplicity's sake, it removes information in order to convey those molecules quicker to the observer. So like I said, most students struggle with these here, so I'm mainly going to be drawing out condensed structural formulas. But be careful when you are drawing molecules. A very common mistake is ensuring your carbons have 4 different bonds. Lots of students will screw that up and they will draw carbons with 7 bonds, right? They'll add in, maybe another hydrogen here. They'll say CH3 here. Well, now this carbon has 5 different bonds, right? Maybe they'll draw a substituent group here and they'll forget to get rid of one of those one of those hydrogens, and again, you now have 5 different bonds. So always double check to make sure each of your carbons is bonded to 4 different things. So just a brief refresher, molecular formulas represent exactly how many of each atom are in your compound. The empirical formula is going to be the lowest ratio of elements in your compound. Condensed formula, which I'm pretty much going to be using, shows you the bonding structure in a condensed way. Then you have displayed formula or complete structural formulas. Again, a little bit more inefficient because you're drawing out every single covalent bond, and that's what those lines mean. Every single one of these lines represents a pair of shared electrons. And then lastly, you have the skeletal or line formula drawings, and these are the least information giving, yet they are probably the most efficient to draw. I will accept any of them as answers. So if I ask you to illustrate a compound, you can use complete structural formulas, you can use line drawings, or condensed structural formulas. All of those are acceptable means. Now the last thing we're going to be talking about today, saturated versus unsaturated. Now in biology, what was a saturated fat? Do you guys remember? What is a saturated fat? A saturated fat has all single carbon-carbon bonds, and each carbon has the maximum number of hydrogens possible bonded to it. And in organic chemistry, that means it means the exact same thing. Right? A saturated hydrocarbon has as many single bonds as possible. Now, what about an unsaturated fat? Right? That had one or more double bonds. In organic chemistry, that's going to be a hydrocarbon that has one or more double or triple bonds within that molecule. So again, we will be using those words saturated and unsaturated when talking about hydrocarbons. So that's it for today. We will be jumping into hydrocarbon naming starting next lesson. Have a wonderful day, everyone.